Okay, so we're going to be moving into module number 3 here now, which is velocity analysis. If we look at the velocity analysis learning plan, you'll notice a couple things. First of all, what we're going to focus on today is going to be the first presentation, or if you would, part 1 of this module. And then we're also going to be referencing this handout. So if you happen to not be in the room and you wanted to reference that, you can pull it up and either take notes or maybe print it out before we get there. But we're going to do a little talking first, and then we'll look at this handout, or at least the first part of it. For those who happen to be in the room, I have it up on the table here, so you can grab it when we get to it. So if you would just we're going to use this PowerPoint to guide us through our chapter. As you know, there's always a little bit more in the chapter than what we're going to cover. So anything that's in our PowerPoint is what you're responsible for, if you will. So we're going to get started here by looking at, like I said, chapter 6, and starting here at the beginning. Our objectives are going to be defining linear, rotational, and relative velocities. So we're going to be really kind of looking at all 3 of these as we move through chapter 3. Linear and rotational, those are going to be the upfront, are going to be like the first half, if you would, and then relatives are going to be the second half. We're going to learn how to convert between linear and angular velocities, and being able to kind of, identify their components, their units, and then also doing some conversions there as well. Apply the relative velocity method to graphically solve for the velocity of a point on a link, knowing the velocity of another link. Okay, relative velocities are where we're going to start looking at like 4-bar mechanisms, and when we rotate the crank, what's happening velocity wise on the other links. And then we're going to use that relative velocity method to graphically show the velocity of a point of interest on what we're going to find out is called a floating link. Okay, so that's the stuff that we're going to be doing here in chapter 6. So as we look at the beginning here, and we look at the introduction, when we look at velocity analysis, we're going to be interested in how fast are certain points on a link traveling. And most often we're going to be interested in what is the fastest point. And normally that's going to be like endpoints or the joints where they come together. Okay, so the determination of the velocity on a link is the purpose really of this chapter. And we're going to be using relative velocity method when we have linkages or more than one link connected to each other. So like those 4-bar mechanisms, we're going to kind of bring those back. So let's talk about linear velocity. So linear velocity, which has the symbol V, is straight line displacement of a point per unit of time. Okay, per unit of time. So velocity's equation is going to be equal to R divided by T. Now, R is the variable that this book started to use when it updated to a new version, to the latest version that we have here. And R is really just the displacement or the distance for which we're going to travel within the amount of time in the denominator there. So velocity has units of distance divided by time. Okay, so for instance, velocity is going to be in, as you can see here, feet per second, or maybe inches per second. Another one might be kilometers per hour or miles per hour. So anything that is going to be a distance divided by or in terms of unit time measurement is going to be a velocity. Okay, for those who have had physics already, this sounds familiar to us, right? You guys talked about that. Now R, they're using the variable R for displacement. It's probably a little bit more familiar to use a D or an S. D for distance is a lot of times how we see it. So we usually say velocity is equal to distance divided by time. They're using R for that distance variable. Now velocity is a vector. Okay, and that's why we talked about vectors just before we were talking now about velocity. So velocity is a vector, and to fully define it, we need to know what its magnitude, usually through an equation like this. How much distance are we covering over how much time? And then we're going to represent it with a vector. So a line with an arrowhead on it, so we know and we identify what is its direction. Okay, so magnitude is going to be its length when we draw it to scale. imagine AutoCAD, and then its direction is going to be the angles and or the arrowheads. Now, rectilinear motion is when we have straight line displacement, okay? So rectilinear motion, which is identified by that very same straight line velocity equation, r divided by t. And we're going to be looking at a very, kind of common, very simple application or example. And this is problem 6.1 in our book. And it's going to be found at the very top of page 124, right there, okay? And here it says, crates on a conveyor are shown in this figure. So we see them there. And they move towards the left. So you'll notice that the velocity vector there, line with arrowhead, is showing us the direction that this is moving. And it's moving at a constant rate, So tell me, what does constant rate mean to you? When you hear constant rate, what is that telling me? Go ahead. It is not accelerating or decelerating. So as time passes by, this is going at a constant rate or at a steady speed. And so when they're telling us that it takes 40 seconds for this to traverse 25 feet, that means the first 40 seconds, we would have moved 25. The second 40 seconds, another 25, and so on. And it's going steady, 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 steady. It's not speeding up. It's not slowing down. Okay, no acceleration or deceleration. So what we want to do is we want to determine what is the linear velocity of that crate. What is the linear velocity of that crate? So using the equation, now I'm just gonna, they have it here, but the velocity equation that we're going to be referencing is going to be this one right here. Velocity is equal to, so V is equal to, V is the variable for velocity, R is going to be the variable for distance, and then T is going to be the time. So in our problem, we got to kind of line these things up. So in our problem, they want us to determine what the velocity is. And as we read the problem, the distance that they're speaking of would be the 25 feet that they're giving us, right? And then the time is going to be the 40 seconds. But when we specify velocity or, any type of rate of, speed, we want to know in units of time. So we don't want to say, oh, this is 25 feet per 40 seconds. We're probably going to want to know how many feet per second it is. So down to the single second, how many feet would we cover in that 1 second rather than the total of 40. Okay. So if we go underneath here, hold on, I don't think I have just blank paper, so I'll use my notebook. Okay. Zoom out a little bit. So for this example, I would start by writing my equation. V is equal to, I'm going to default to, I'm not crazy about the variable R because that's not like normal to me and it's not very common either. I'm not sure why they use R, quite honestly, but I am simply going to say D over T. Okay. Now, when we write our equations, I'm going to encourage you. That means that you need to do it this way. For you to write them in their top-down fractional form. Do not write this in D/T, like in a horizontal line, like you're typing it out, okay? You'll notice that in my PowerPoint sometimes just because, on a keyboard, that's easy to do, or you'll notice it in the book that way, maybe listed. But when we're showing our work for calculations, which you will need to do, you need to write it in numerator on top, denominator on the bottom, okay? And you'll always show me first and foremost the equation in variable form. It's kind of like you're telling me what you're going to do before you do it. Okay. So in this case, we're going to be calculating or determining what the velocity is. And the equation for determining velocity is distance divided by time. Okay. Distance divided by time. So now what we can do is from our problem, find out and plug in our values. So we know our distance is going to be the 25 feet. And we know that it doesn't say the distance is 25 feet for this equation, but this is where knowing units is really important. So I have to presume that at this point, you kind of already know, standard types of units for instance, distance. So because it says 25 feet here, that's going to be the distance in the equation we're looking. Additionally, when we're looking at time, we're probably going to be getting a time in seconds, minutes, hours, whatever it might be. And then we're going to use that variable or that number for the variable that we're going to be, plugging it in for in our equation. So as we look here in our problem statement, 25 is going to be our distance and our time is going to be the 40 seconds. Okay. So now you'll notice that we're going to be right next to it or below it, however you want, but you have to show your work for me so that number one, I can read it and then it's followable, if you would. So I'm going to put 25 feet on top divided by 40 seconds. Okay. Now, you guys are new to me. The next thing that I'm going to be looking for is that you put the units in all phases of the problem. That means if you leave the feet and the seconds off here, you will get points off on your problem. Okay. You have to put the units in all phases of the problem. So equation in variable form, just like we see it here. And then we're going to put our values in with their units. Okay. And then at this point, we would cancel out any units that would maybe be top to bottom. But in this case, nothing cancels out. And then we look, before we even do our calculation, what I encourage you to do is look, what are the units that we're getting? We're getting, in this case, feet over time or feet over seconds. So that means it's feet per second, right? Are those normal units? Are those expected units for the quantity we're solving for, which is velocity? Distance over time, feet per second. Does that seem like it's a good set of units for a velocity? Yeah, okay. And the reason I have you do that is so that you can do exactly that. You can look at what are the units that are left here so that you can make the determination, are those the units that I'm expecting? If they're the units you're expecting, then you set up the problem correctly, because I'm going to tell you 95% of the time when students get a problem wrong, it's because they didn't put the right thing top or bottom. So if you would have mixed up the 40 and the 25 without putting the units in back of it, you wouldn't have ever known. And then if you sneak the units in at the end, that's not showing your units in all phases of the problem. Okay. So you would get points off. I'm just telling you, if you do 25 over 40 and then just, give me your answer, and then all of a sudden feet per second, magically shows up. Okay. So I'm gonna calculate then my velocity here. I always put the little tail on the V for velocity. They use capital V, which is fine. To me, capital V is volume. I don't know. And this is kind of like that lowercase cursive V, if you would. All right. So now to determine this value, I'm going to take 25 divided by 40. What do you guys get for that number? So bring your calculators. 0.625. Okay, so 0.625. Is that my final answer? Feet per second. Exactly. You need to add your units here as well. So this is going to be feet per second. And then you're going to put a box around your answer. This is how I would be expecting any calculations that you do for me in kinematics. Okay, anything that is going to be something you have to write out and calculate, you have to show me that work. So equation in variable form, the numbers in place with their units in all phases of the problem. At this point, you would do any cancellations, but then also what's not canceled, feet per second, are those going to be units that are expected for a velocity? And then you do the math, and then you put your units, and then also do this for me too. Don't just like put a box around 0.625 feet per second. Tell me what variable you're solving for. So in this case, you're solving for the velocity. What's the velocity? Your answer, your complete answer should be V is equal to 0.625 feet per second. Okay, with the box around that. Don't shortcut it and just put a box around this. I take points off. Okay, I know. You're thinking right now, that is so ticky-tack. It's okay. That's all right. When you get out in industry, companies are going to have expectations of how they want things done. All right. So this is how I want it done. And the reason I want it like this is for really a couple really good reasons. Number one, when we do our unit assessment, and that's going to be coming up actually after velocity. When we do that unit assessment, you have open book, open note. And if you have your procedure written out like this, it's really easy to follow, okay, for you. Second of all, when you hand this in, if I can't read it, I'm not even gonna try to squint and try to figure out and see. I just move on and you get a 0 on it. I don't give any points. So it's going to be a neat format that I can follow. Okay. Additionally, when your units come out the way they're supposed to, you know you had it set up originally correctly. Okay. So that's that. And then put a box around your final answer to say, this is the answer to that question that was asked. Okay. And label it with the variable that you're solving for as well. So again, V is equal to, in this case, 0.625 feet per second. Okay. So part of what I do here in lecture, this is why it's important not to jump to the homework. Part of what I do here in lecture is clue you in on that stuff, because otherwise you're going to be getting, a lot of points off, and then you're going to have to do the assignment again. All right. So to be efficient, it's important to, pay attention during the lectures and then apply this stuff when you do your homework. Okay. And then let's just kind of finish up here. So we have, we determined it. They put their values in here. We can compare 0.625 feet per second. Okay. But then they did a conversion. So depending on the units that you might, want, or that might be asked of you, then we would need to do a conversion here. So let's show this conversion. Now, in this case, it's just, multiplying by 12, but if you do a conversion, I also want to see that too. Okay. Don't just magically come up with a number. So, so in this case, if I have 0.625 feet per second, okay, your units need to be top bottom when we're doing conversions, especially. Okay. If you put a final answer in feet per second here, I'm okay with that, because you're not going to be using it anymore for any other parts of the equation. But if you're doing a conversion, we do need to go numerator, denominator. Okay. Numerator, denominator. So you'll notice here, I have this top bottom. Now, when I do conversions, and this is going to be like your foolproof method, and we're going to continue to kind of reinforce this. You may or may not have seen this before. I think it's referred to as the ratio method. Okay. So what we're going to do is I'm going to put a vertical line and then a horizontal line, and this is going to be numerator, denominator. Okay. And we're going to be multiplying across the top and dividing by the bottom. And in this area right here, we're going to do a conversion. And now I look at, in this case, we want to convert this to inches per second. So the bottom is already in the units that I need it to be in, right? The time. So I don't need to worry about that one. But the feet, I need to convert to inches. You might say, well, I just multiply by 12, or I just divide by 12, whatever. Be careful, okay? Because what if you do the wrong thing and you did it in your head, and then you've got a number, and all of a sudden, do you really know if it's correct or not? Okay. I don't know. So the way that you can do this so that it's always going to work out is this ratio method that we have here. So if I want to convert the feet to inches, as I know, when I multiply across the top, divide by the bottom, if something is on the bottom and this is on the top, I get to cancel it out, right? So I want to get rid of feet. So that means I'm going to put 1 foot on the bottom down here, and directly above it in this ratio, I am going to put how many inches are in a foot. How many inches? Tell me what to put on top. 12, exactly. So I'm going to put 12 inches on top with its units. Okay. Now, this right here, I use vertical lines for signifying that I'm doing a unit conversion, that it's not like an equation that I'm multiplying things. You'll notice that the book did this very same conversion, but they used the regular rounded parentheses. This is something that I learned years ago from, somebody else. And it was probably around that first time when I was doing, learning conversions myself, or at least getting a good method to do it. And I've done it ever since. And this is how I teach it. It helps. We can put these conversions right into equations. And when I have the vertical lines instead of parentheses, it kind of separates them as, oh, that's just the conversion part of the problem. You kind of know what those numbers are then, as opposed to when you have variables that have actual, numbers themselves rather than conversions. So now when I multiply across the top, divide by the bottom, I can cancel out. And this is what you would do in any conversions that you do as well. Show the units canceled out. And now you look at what's left. On top, I have inches left. And on the bottom, I have seconds. So if I'm wanting to convert 2 inches per second, that's as far as I need to go with my conversion. So now I'm going to take the numbers that are on the top. I'm going to take 0.625 times 12. And what is that number? 7.5, okay? And then my units that are left over are on top, inches, right? And on the bottom, seconds. So this is going to be inches. You can put per second if you want, like as a slash, as a final answer, if you're not going to be continuing to use it, okay? And then this would be equal to your velocity. So we have it just converted in that second case, okay? How many have seen conversions done like that before? Good, 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 good. Okay. If not, you're going to love it. You are. It's going to be, you're going to be like, oh, you know how, and I always, okay, you may or may not be like suspicious of unit conversions, but I always am uneasy when I go online, for instance, and I'm like, okay, how do I figure out that, you know, how many quarts are in a gallon? And it says to multiply by this number. I don't know. I never like trust it. This foolproof, absolutely foolproof. Because now I'm not wondering, am I multiplying by the number? Am I dividing by the number? Should my final answer be higher or lower than whatever I did? I don't have to rely on that. All I got to know is 1 or 2 simple conversions, and I can put them top bottom. And then if the units work out and I multiply across the top, divide by the bottom, done. I don't have to, you know, worry if I did the right operator. Additionally, with the units here, you can see exactly what cancels out and what stays. And you don't have to, like, you know, multiply by this number and then like just kind of put the final units in and kind of, you know, cross your fingers and hope for the best. All right. I want you to be really confident about that. If there's one question that you can ask me that I'll be always like, oh, well, I'm always happy to answer any questions, but it's a great question to ask. How do you get the units to work out for this problem? Okay. And we'll always stop what we're doing and we'll do that. Okay. Because that's important. And I want you to pay attention to that, because again, if you end up with the right units, top bottom, for a quantity that you know is going to be distance over time, and I'm distance over time here, now I know my setup was correct. And that's all the problem. That's it, right? And then it's a matter of just plugging and chugging the numbers and putting it on your calculator. Okay. So it might have taken a little while to do that, but there's kind of a lot there as far as expectations for what you'll be handing in for me. Okay. All right. Showing your work. This is what it looks like. This is what it looks like. Okay. So hopefully you're used to that. If not, you're going to love this. It's good. It's good. Okay. All right. Let's go back. So that's that problem. Let's talk a little bit more about linear velocity. So linear velocity of a general point. Okay. And we're going to look at figure 6.2, which is on that very same page, but a little bit further down below. And there are points A and B on that link. Okay. Now you're going to notice that they're on the same link, and we're going to see that the link is rotating in space. Okay. But there's going to be a linear, what we call linear component of the motion for each one of those points that are identified there. Now, the second statement here says the points that are further from the pivot or the center of rotation, they're going to actually travel faster linearly than points that are closer to the center of rotation. Okay, so let's take a peek at that figure. Okay, so it's this figure right here. Okay, figure 6.2. Okay, so we have a link here. So this looks like, you know, a potential link that we would have put in one of our 4-bar mechanisms, right? So we've got what we could say would be link number 1, which is the frame not moving. And this link is connected to the frame by a pin. And you'll notice that it's kind of this triangle shape. So it must have some sort of, you know, thickness that's important to us. We have points A and B identified. Okay, so those are points actually on the link, not, you know, by the joint in this case. So they have point A, point B there. Okay. And then you'll notice this arrow down here. Okay, that arrow that's going kind of around that circle there and labeled with the W2, that signifies its rotational speed. Rotational speed. So the sub 2 means the rotational speed of link number 2. Okay. And what's happening is that link is rotating. It's a fixed center rotating about the frame here. All right. And then you'll see that we have a couple points that are identified on that link. So the entire link is rotating at 100 RPMs. Okay. And so it's going to be going around 100 times in a minute, for instance. Okay. Now, along the length of that link, that's why we're looking at A and we're looking at B. Along the length of that beam, or along the length of that link, we can have, infinite number of points, but we have A and B identified here. And you'll notice that coming from A and B, they have a velocity, okay? When we look at that velocity, it's not going in a circle, right? It's not going in a rotation. It's actually capital V, which is rectilinear or linear velocity. Linear velocity, meaning it's going in a straight line. But that link, which points A and B are on, are going in a circle, okay? So any point along a link that is rotating not only has rotational motion or speed, W, it also has a component of straight line velocity, okay? Imagine if this is rotating, and let's say point A was not affixed and point B was not affixed, but it's on there right now. And all of a sudden that link is going to like stop, okay? Suddenly stop. And A and B are not affixed to the link, so they're going to continue moving. The V vectors here show us the motion that they're going to take. They are not going to continue to go in a circle, because by being on the link and rotating about that center, that keeps it in a circular path. But as soon as they don't have to be on there anymore, meaning it stops suddenly and they're going to continue, they are going to continue in a straight line. They're going to continue in a straight line. And that's what this straight line motion, or this straight line velocity component of that point, represents. Okay. Now at the center right here, there is no straight line velocity, because it's not, that's the center of rotation. But as soon as we start moving away, now all of a sudden we have straight line velocity. Okay. Straight line velocity. Now, how much? Okay. How much we have, we're going to be using an equation, and that equation we're going to find out is going to relate its distance away from its center of rotation. Okay, so before we look at the equation, just want to draw you a little diagram here. Okay. So if I take frame member, and I'm going to kind of show the same type of link, but I'm just going to show it as a straight line. So here's my point B, here's my point A, or we can do A along the length. We'll just do it along the very same length. And this is going to be point A. We're going to be rotating in a clockwise manner. So we'll call this W2, just like in our example. And what we find is we have what we call a proportional relationship of the straight line velocity to its distance from the center of rotation. So if I look at the linear velocity component of B, this would be a representation, we would say VB right here, of the amount of linear velocity at point B compared to any other point along that distance. So this would be VA. We would have another point down here. This would be, we'll call this point C. This would be velocity of C. So what you'll notice here is that as we move further away from that center of rotation, our linear velocity component increases, okay? Now, I know all of you have been to the playground, and as a kid, you rode on, and maybe even as an adult, you rode on the merry-go-round, okay? It's a perfect example of a merry-go-round. So if we look at a merry-go-round, okay, and I have my center of rotation here, this is top view, okay? And I'm going to be going around my merry-go-round here, okay? And imagine, I'm just kind of like, this is just the radius out. This is just a line I'm drawing, okay? And on the very end here, this would be my point B. Like right about here would be my point A. And then this would be the center of rotation, okay? Now, if we take this very same concept and we kind of like go out like this and we show the velocity, Okay, this would be the velocity of B. This would be the velocity of A. Okay. You'll notice that it's longer out at that edge of my merry-go-round, right? Now, can you relate to that? Can you relate to that? Thinking back to when you would go on the merry-go-round and you would maybe sit on the edge as opposed to sitting closer to the center. How was that experience maybe different?
More fun on the outside.
Alan said it was more fun on the outside. Yes, and I heard something else. It takes more effort because it actually takes more, if you would, more force to keep you on. But as soon as you're not able to hold on anymore or whatever, what happens? You kind of, it's more fun out here. You're going faster, right? Linearly. And then let's say you fall off. What's the direction you fall off? Do you keep tumbling in a circle? No, you're gonna go this way, right? The big kids always sat at the perimeter, right? The little kids, we always put it that, well, the moms did. We put them at the inside, right? They were safer there because they weren't going as fast and they weren't going to fall off like the big kids. But the little kids always wanted to be with the big kids, right? So you didn't want to, okay, fine, but you had to sit here. So that's what's going on there. And that linear velocity component is going to increase as that distance also increases. Okay. Now there are other situations that this comes up on. Can anybody think of any other place that you may see this? I know, sometimes putting you on the spot for examples. Has anybody ever played? Now, this was something we did as kids when I was like in middle school, and we would go ice skating. And these are things that, again, don't happen nowadays. They used to happen back in the 80s. And when we had a big field in the back of our middle school, and they would flood it in the winter so that we could all go ice skating during our recess. So you would bring your ice skates every day. And during the winter, we would go ice skating. And something that we would do is we would form a long line, and the person in the front, it was called crack the whip. And we would play crack the whip, and you would, skate really fast. You would get the whole line of people. You would hang, one person in back, kind of like a train of people holding on to each other. And then what would happen is the first person would stop and turn really suddenly, and that whole trail of people, kind of like the tail, would then be going, and what would happen is the people, as you go further and further out, you're moving faster because of exactly this. Okay, here's the person that's leading the whole line of ice skaters. And then those people are ice skating on the outside here. They're going a lot faster. And then eventually you can't hang on, and it's just kind of fun, right? So that's another kind of example, if you've ever had that. Some people have said that they did that on roller skates, where you kind of played that very same game. Does anybody else have any experience with that? No. See, we didn't have video games when I was young. We had to figure out fun things to do. But anyway. So that's just another way that you might relate to this concept. Now, let's look at direction, okay? The direction of that straight line velocity is defined for us. Number one, it's going to go in the direction of the rotation of the actual link, or in this case, on the right-hand side, the merry-go-round, okay? So if I'm rotating clockwise here, anytime I even specify maybe another radius, whenever I look at, and I'll kind of put B prime here, okay, B prime, this velocity is now going to change and go like this. So this would be VB prime. Do you see anything about those directions that seem to be common? This would be A prime, so this would be VBA prime. Do you notice anything about those directions, even as they move from one point to another, or one place on that rotational, or from one angle, I'll say, one angle to another? Perpendicular to what? They're perpendicular right here. They're perpendicular to this line. What is that line do you think that's called? we call it the radius of rotation. Okay, so for this point, this is its distance or its radius from the center of rotation. All right. And our velocity will always be perpendicular to the radius of rotation, and it will always be directed in the direction of rotation. Okay. So if I take a line and I go over here and I put my v prime prime, my velocity, it's going to be going around in a circle here, is going to be perpendicular to that line. Okay, perpendicular to that line, and it's going to be going in the direction of rotation. Okay, and this would be its radius back. Okay, so let's look at the equation to solve for what's the relationship between rotational speed, velocity, and this radius. Okay, let's see how they're related. It's going to be on the shoots. Thought it was going to be right here. Dang it. I was like building up to this. Where is the equation? Dang it. That's all right. Forget you. Here it is. It's on the very next page. I knew it wasn't far in the book, but I'm not seeing it on my PowerPoint. Maybe it's further along. So if we look back underneath on the book on page 26, right underneath here. Okay. This is our equation that relates straight line velocity, that radius back to the center of rotation, and our angular velocity or the rotation of that link. Okay. So let's put this underneath. And let's kind of start, if you would, an equation sheet just to kind of organize what we have here as we're going through. So we already identified our straight line velocity is distance over time, either d over t, I'm always going to default to that, or r over t, same thing. D and r are the same thing. And sometimes you may see it as s is another way that we see it. Okay. Now the units, it's always important to know the units. The units are going to be, for instance, inches per second. Okay. Or feet per second. Or meters per second, you know, things like that. Any distance divided by time. Okay, these are ors. And the newest one we got now is going to be V is equal to R times W. Okay, R times W. Now, let's identify each one of these over here on the side. So we know that V is equal to velocity. Okay. D is equal to time. No, it's not. I was thinking D is equal to distance. Okay. T is equal to time. All right. And now down here, V is still velocity. Okay. R, lowercase r, not uppercase r, lowercase r is going to be radius. And that's going to be reference to the radius of rotation. And then W is going to be angular velocity. Angular velocity, sorry. Now, for the first three, we already kind of have their units down. We know that distance is going to be inches, feet, meters, kilometers, miles, stuff like that. Time is going to be seconds, minutes, hours. Those are familiar to us. So velocity has to be, and we've seen this before, distance over time. So it's going to be whatever units we're dealing with, inch per second, feet per second, meters per second, kilometers per hour. Okay. Down here, same thing. We're still expecting distance over time. Okay. Distance over time for our velocity. But now radius, what are we expecting for that? So radius, if we look back at that illustration here, this is my radius. What type of units would I expect for that? Inches, feet, meters, right? Yeah, it's another form of a distance, right? So we would be expecting, we would be expecting for our radius to be in, I'm gonna put inches, you know, just for a form of. Angular velocity. Angular velocity. Now, angular velocity is when I've got the entire thing rotating. What are units you think for angular velocity? Go ahead. I heard, oh, good. What were you gonna say?
Reading per minute.
Oh my goodness, you guys are jumping to where I was like going to go. But first of all, revolutions per minute, RPMs, okay? That's gonna be one of the set of units. So I'm gonna put this down here. So this is gonna be, whoopsie. So sorry. This is gonna be RPMs, okay? Revolutions per minute. That's going to be how fast it's going. And when we talk revolutions per minute, it's something we can relate to. So if I'm going 1 revolution per minute on anything, that's kind of slow, right? To go all the way around, it's going to take me 60 seconds to do that. It's pretty slow. But if we start talking 1750 RPMs, 1750 revolutions per minute, now we're going a little bit faster, right? Now we're going a little bit faster where we got to make, 1750 complete revolutions in 1 minute. Okay. That's like motor speed. That's like motor speed, typical motor. Okay. Mitchell and Jacob, right? Mitchell and Jacob had mentioned radians per second. Okay. Radians per second. Absolutely. That's another form of units that we use for rotational motion. Now, in and out of this equation, it has to be radians per second. It has to be. So if we are given RPMs, like how fast is the straight line velocity of something sitting 2 feet from the center of a rotating disc going 10 RPMs, you're always going to get it in RPMs. Before we can put it in this equation, we have to convert to radians per second. So we'll be practicing that in just a bit, okay? Right. So in and out of this equation, this has to be in, I'm going to use inches per second. That would mean that my radius has to be in inches. And that would mean that my W has to be in radians per second. Okay, radians per second. And when if I'm solving for W out of this equation, so if I'm rearranging and solving for it, it's going to be radians per second out of there as well. And if I give you a problem and say, what is the rotational speed of, what is the final rotational speed of this link when we have, V equals this and R equals that? You're going to use this equation. You're going to solve for our W, and the final units are going to be radians per second. Radians per second, but you're never going to leave that as your final answer because nobody relates to radians per second. You wouldn't go to the motor store and say, I'd like a motor that is going to perform for me at 245.8 radians per second. They're going to be like, what? You have to convert it to RPMs. So always we want to convert those then to units that we could, converse with and relate to. All right. Okay. Does this look familiar to you guys? Probably from physics as well, right? Yeah. So yeah, it's a application of. Now, to kind of reinforce this and to bring all of this back, because this is really important in terms of units and then doing these conversions. And then also what are the directions of the velocities in relationship to the rotations. That's what my handout is. That's what my handout or my worksheet is. So we're just going to kind of go away from our PowerPoint and the book for a little bit because the book doesn't spend much time here at all. Okay. And it is really important, especially in the problems that they're expecting us to do. So if you're in the room and you want to grab a handout from the front of the room here, and if you're following along, you'll just either want to take notes, or if you happen to get it printed, great. I can give you a little bit of time to do that, but I'll have you follow along with this because there's going to be points here that there's going to be information, but kind of as a review of what we just looked at, but then also there's going to be some things to fill in. So on the front here, this is kind of like your kind of review, if you would, of linear velocity. So we know that linear velocity is, like I said, I always use D or S. The book used to use S. So the version before this one, when they did this new update or this new edition, it was always S. And then in your physics classes, you'll normally see it as D. So you'll see me do D and S most often. So here's S. So this is also equal to D over T. So it can be that very same unit. So distance. So rectilinear velocity can be that conveyor belt, maybe a car moving down the road, just looking at it, going past us, a person walking a distance. Those are all linear velocities. Okay, linear velocities. And we would be defining those by, or calculating those by, how much distance did that thing or that person cover in what amount of time. Okay. So like our example before with the conveyor, we went 25 feet in 40 seconds. Okay. And then you would divide 25 by 40 to get 0.625. And then it's feet per second, looking at it per unit of time. Okay. And then we looked at, a similar example to this. So velocities on a single rotating link. Okay. So if we have a link connected to a frame, in this case, we've got the frame identified as number 1. Number 2 is going to be our link. And we have different points along the length of that link, X, Y, and Z. Notice that we have each one of these linear velocity components to the individual points. The link itself does not have linear velocity. The link itself as a whole will only have rotational velocity, but any point along the link will have a linear velocity component of its motion as it rotates around that center of rotation. Okay. So link number 2 is going to rotate at an angular velocity, always signified by, I think it's the Greek letter omega, lowercase omega, okay, is the W, and they're calling it W2 here. And then it'll always have a direction. So it's going to be either clockwise or counterclockwise. So angular velocity is a rotational speed, clockwise, counterclockwise. And in this case, it's going to be depicted, based on the link that it's on. In this case, it's link number 2. So it's W sub 2. Points X, Y, and Z have linear velocities, as we said earlier, Vx, Vy, and Vz. The direction of those linear velocities, as you can see, and as identified in this little paragraph here, says the direction of the linear velocities is always going to be pointing in a straight line in the direction of rotation and always perpendicular to the radius back to the center of rotation. Okay, so if this point X, here's its radius back to its center of rotation, it's the straight line, its velocity is going to go in the direction of rotation perpendicular to that radius. Same thing for Y, same thing for Z. Okay. Turning the page. Here's some fill in the blanks. Okay. So as we look at units, that is something that is a huge emphasis that I put on every one of the classes that I have. So if there's anything where you have to do any calculations for me, we're going to be like deciphering units. So it's always important to know what we expect the final units to be for, in this case, straight line velocity, which is V. What do we expect those units to be? You tell me. And they can be various units sometimes, right? What would we put here? And this is like a fraction. So numerator, denominator. What would I put on top for the units for straight line velocity? It's going to be distance over time. I don't want that, but I want units. What are units that I would put on top, for instance? Miles per hour. What else could I put? Inches per second. What else could I put? What? Oh, lights per year. Light year, right? Yeah, so anything that is going to be distance divided by time. Now, when we're looking at kind of like machinery, common units are either going to be inches per second or feet per second. Okay, in kinematics, we're always dealing with English units. In physics, you're probably always dealing with the metric, right? That's what we did when I taught it. So feet per minute, or feet per second, inches per, I'm just going to put inches per second. I don't have much room in here. inches per second as an example of distance divided by time. Radius, since it's a distance, what would I expect those units to be? Inches, feet, meters, millimeters, miles, kilometers. We're going to use inches. Okay. Angular velocity, W. Units here. Well, there you go. Numerator, denominator, revolutions per minute. Okay. Revolutions per minute. And then what was the other one you said before too? We'll put that one over here as well. We'll put it on this side. Radians per second, right? Now, in this equation right here, this is a rearrangement of our base equation. So on the previous page, our base equation is V is equal to W times R, right? If I want to solve for, and I want to rearrange this algebraically for W, or the angular velocity, this is simply that rearrangement. It's going to be W is equal to V divided by R. Okay. So now let's put the units on top for velocity, the units on bottom for the radius, and see what we get for the units. Make sure that they're radians per second. So on the top, we're going to use inches per second. On the bottom, we're going to use what? Inches. Okay. So algebraically, when I just look at the units here, and that's what those brackets are. They're signifying I'm going to put my units in there. That's why I have these brackets instead of parentheses. Notice that top to bottom here, my inches cancel out, right? And I end up with nothing per second. Or how come I have radians per second written here? Where did the radians come from? The nothing per second. Radians are unitless, right? I'm just kind of chuckling because now is where this is something I always said every year to my students. Radians are like Lucky Charms. Okay. Why do you think they're like Lucky Charms? You tell me. They are magically delicious. Well, maybe not the radians, but Lucky Charms definitely are. They magically appear and they magically disappear. So when it's nothing per second, they magically appear, radians per second. Or when radians end up being multiplied by something else, we don't say a radian inch. What do we say? Just say inches. But the radians were there. They magically disappear. Okay. And they may be magically delicious. I don't know. Just saying. Couple times over the years, all of a sudden, randomly, boxes of Lucky Charms would land on my desk at school. And I'd be like, aw, people were listening. So just saying, I am a fan of the Lucky Charm. I do like that cereal, but anyway. Okay, so any questions about units? I mean, that's really kind of the whole point here. Any questions about units? Okay. How many have seen this before, know and understand? They're like, oh, this is totally review, Kelly. I'm totally bored. Oh, not yet. Okay, good. So some of it might be new, like bits and pieces are probably familiar, but maybe putting it together, you haven't maybe seen. And I'm pretty sure nobody said that radians were like Lucky Charms. So that's new. Go ahead.
How do we go from seconds on top to seconds on bottom?
Oh, you mean up here?
Yeah.
Remember, and this is going to be an algebra thing, and I just didn't write it out the way that probably you did in algebra. So when you divide, right? When you divide, what you're going to do is, so for instance, I'm going to take and I'm going to say inches per second, and I'm going to say times 1 over whatever that denominator is, right? Is what we do in algebra technically. So that's going to be 1 over inches. So instead of doing it top bottom, if we multiply it, horizontally like this, the inches cancel here. So you end up with nothing over seconds. Does that make sense? Yeah. You're welcome. You're welcome. Good. Yeah, always ask. Never hesitate to ask about units and how we get something, because that's an important part of what we do. And it's, again, the verification of that you set things up correctly. And that's the biggest part of the problems. Okay. All right. So many times our W is going to be given to us in RPMs or revolutions per minute. We need to convert it to radians per second so that we can put it into this equation or get it out. Okay. So if we're solving for a velocity, for instance, and our problem says that our link is moving at 200 RPMs, we can't use that 200 RPMs here. We have to convert it into radians per second before we use it in here. So the practice that we do right here is going to be a little bit of that conversion stuff. So we're going to start with 500 RPMs, and we want to convert it to radians per second. So here are our blinks. We have 500 revolutions per minute. Notice we're not writing it as RPMs. I want to expand out and put revolutions on top, per minute on the bottom, and the 500 is in the denominator because the 500 is our whole number, if you would. But then our revolutions per minute are going to be written top bottom. Then my vertical lines, again, that just signifies that I'm going to be doing a unit conversion here as opposed to, you know, an equation, if you would. All right. So I want to convert this to radians per second. So we know that our process is going to be multiplying across the top. So it's going to be this times this times this divided by whatever on the bottom. Now, when we want to cancel something, okay, we want to then make sure that whatever that unit is, for instance, revolutions, we want to get it to radians, right? We're going to start with revolutions, and we're going to say, oh, if revolutions is on the top, I'm going to put revolutions on the bottom in the very next spot. That way, when I multiply across the top, divide by the bottom, revolutions cancel out. Okay. Now I need to know how many radians are in one revolution. Do you guys remember that? 2 pi radians. That is so good. So one revolution is equal to and directly above or below, whichever way it ends up going, I'm going to go 2 pi radians. Okay. So now I can do the cancellation right away. If I multiply across the top, divide by the bottom, my revolutions cancel out. And now I'm in, what's left over is radians per second, or I'm sorry, radians per minute. So I still need to do a little bit because I got to get my minutes into seconds. Notice that my minutes are on the bottom. So am I going to put it in the top or the bottom here in this last section? Going to go in the top, right? Minutes are going to go in the top. Oopsie. Minutes. And seconds are going to go in the bottom. What are my numbers? 1 on top and what on the bottom? 60 seconds. Oh. And then as I look here, multiply across the top, divide by the bottom, minutes cancel. What's not canceled? Radians on top, seconds on the bottom. So radians per second, right? So now I'm ready to do my multiplying across the top, divide by the bottom. What's your number that you end up getting? Say it again. 52.3. Can somebody confirm that? We should all have our calculators out, excited to do this work. 52.4. If you round up, is that right? Eric, do you concur? Okay, 52.4. Anybody else get 52.4? How about those who are virtual? You got it? Okay. All right. So any questions on that? That again should be pretty familiar. The process that we're using, got it. Okay, thank you, Jason. The process that we're using might be a little different. Okay, I'm not gonna, you know, this was shown to me years ago. I've seen it in some textbooks and some I don't. All right, so I'm not saying it's the way to do it, but it's the foolproof way to do it. You don't have to try to be like, do I divide? Even when I do inches to feet or feet to inches, I'm always like, in my head, if I don't have my calculator, like, I gotta write it out. Do I divide? Do I multiply? I'm not sure. And I don't want to get it wrong, right? So write it out. And that's I'm insistent on. I want to see that. Okay. It's a good habit to get into. I used to teach physics for not only mechanical design, but also electromech. And electromech students, they would grumble at first when I would tell them, I got to see everything. I want you to write it out. I want to see the cancellations. I want to do this. And they would roll their eyes at me. And the mechanical design students are like, yeah, just do it because she's going to take points off. And they would always say to me, well, our other instructors don't require us to do that. I said, well, you're in physics. You got to do it. And by the time they were done and towards the end of physics, they were doing it in their other classes too. And they were like, now it makes more sense when I write these equations out, because even in electromech or even in electrical classes, you've got units and you don't want to just magically, like kind of hope for the best when you get to the end. Did it actually work out? And units will be your clue, right? So I insist on that. You got to write those out for me. And if you do the conversions, you've got to write it out as well and put your units in all phases. So hopefully you're used to that. I hope you're used to that. If not, you get to do it now. So that'll be good. All right, now let's go the opposite direction. Let's go from radians per second to revolutions per minute. Go ahead and do it on your own. And then I'll kind of hang back a little bit and we can compare. Okay, let's start looking at this one. So I tend to always do my numerator first if I need to change it. So in this case, we're in radians per second. We have to get those radians into revolutions. So with the radians on top, I know that in my next section, it's going to go on the bottom, right? So I'm just going to write the units first. Okay. So that if I'm going to put radians on the bottom, that means I'm going to put revolutions on the top. And then I just need to do my numbers, what each one is equal to. So I know, well, you guys tell me what is the conversion between revolutions and radians? Okay, well, so how many radians are in a revolution? 2 pi, right? So 2 pi is equal to 1 revolution. So just like you said, 1 over 2 pi. So 1 revolution over 2 pi radians. That's my ratio. Or I like to say 1 revolution is equal to, and I put it directly below it. Now, when I multiply across the top, divide by the bottom, notice that my radians cancel out here. Need to show that. And what I'm left with is revolutions on top per second. Okay. So when I look at my final units, I need to get this into revolutions per minute. So I've got the revolutions done. Now I need to get my seconds into minutes. This shouldn't be too hard, right? So if the seconds is on the bottom, and that's why we got to go top bottom here. Don't do the slash. So seconds is on the bottom. So that means my seconds is going to go on the top. And then directly below it is going to be my minutes. And now I can just do my conversion. So what would my conversion be here? What would I put on top? 60. And what would I put on the bottom? 1. 1 minute is equal to 60 seconds. And now as I multiply across the top, divide by the bottom, my seconds cancel. And I'm left with revolutions per minute, which is exactly what I'm looking for. So now you want to do the numbers. You want to do 10 times 1 times 60 divided by 2 divided by pi and divided by 1, right? How many revolutions per minute do I end up here when I start with 10 radians per second? 95.5? Anybody else get that? 95.5. So 10 times 60 divided by 2 divided by pi. Seems reasonable. Okay. Any questions then on this page, units and conversion between radians per second and revolutions per minute? Okay. All right. So then let's do a couple example problems. Okay. Couple example problems. Here we have a link number 2 says determine the straight line velocity of point B as line 2 or link 2 rotates 100 RPM counterclockwise. Okay. So counterclockwise means that we are going to be rotating about that center of rotation, and we're going to be going counterclockwise. Okay. We're going to identify that as our W2 because it's the rotational speed of link number 2 or line number 2, however you want to say that. Okay. So W2. So you have to show this on your diagrams. All right. Now we want to know what the straight line velocity is. Straight line velocity of point B. Go ahead and draw the velocity of point B as you would believe it to be. Just go ahead and draw it. And I'll put mine in just a second. Kind of knowing what you know so far. Is velocity of B going to be going up and to the left or down and to the right? Or straight down or straight up? Up and to the left. Correct. Correct. So I should show it, or you should have shown it just like this. Okay. Going up and to the left. Velocity of B, you want to label it, and you need it to be perpendicular to its radius back, or the line back to the center of rotation. Here's that line back to the center of rotation, right? Yeah. Okay. This is the number that we want to determine what it is. Okay. That's going to be what we're solving for. Okay. Now, to get that straight line velocity when it's rotating on a link, our equation is going to be V is equal to RW, or VB is equal to R times W2. And you could probably say radius of 2 if you wanted to too. Okay. So here, my radius from the center of rotation to the point that I want to solve the velocity for is going to be 10 inches. Okay. And then my W2 in my problem says it's 100 RPMs. Okay. So then we just multiply it out and we get our velocity of B, correct? No. No. Not correct. What did I do wrong here? Intentionally. I need to change the units for my W. They can't be in RPM, remember. In and out of this equation, they have to be in radians per second. So I go like this. Shucks. I can't use the 100 yet. I can't. Get it out of there. So before we can put it in there, we need to do our conversion. So I'm going to do just a little bit of a side note here. So we're going to start with our 100 revolutions per minute. Remember, we can't do RPM because we need to see the up down expanded out so we see revolutions per minute. So go ahead and do your conversion, and then you can peek up by me and see if you get the same thing. you should end up with W2 is equal to 10.47 radians per second. Did you guys all get that? I'll let you finish up. Yeah, I got some confirmations in the room here. Those that are online, did you get that same number? Yeah, okay, good. Alan, I see you. Good. All right. That's why we do these in class too. You know, it's not just to just do them, but I want you to get that experience because truly, you know, sometimes, yes, I got it. Great, Jason. Thank you. Because sometimes, you know, you can look at it in the book and see me do them, or even look at the examples in the book. And when it's time for you to like do your problem, you've got a blank piece of paper. It's like, oh crap, where do I start? So this is part of kind of giving you that experience. So, and it also makes lecture go a little bit more interesting than just sitting and watching, right? Okay, so now this is the number I'm going to put up there. Okay, so I'm going to say 10.47 radians per second. 10.47 radians per second. Okay, so when I multiply that out, I'm going to get my VB is equal to 104.7, right? And what are my units? Inch times radians divided by seconds. Inches per second, because what happened to those radians? They did what? Say it. You know, you want to say it. What? They were magically delicious. They are. And they magically disappeared because they're magically delicious. So it is inches per second, not inch radians. They disappear. Okay, they disappear. And then this would be our final answer. We put a box around it. We say VB is equal to its number with the units. Okay, nothing to cancel here. Nothing really to cancel, right? It's just that when we take inches times radians on the top, right? It's just that radians go away. Okay, so good, so good. All right, any questions on that problem? All right, let's do another one. This one, we want to determine the angular velocity of link number 2. Angular velocity of link number 2. So here's link number 2. It is going to rotate about the fixed center A, which is on the frame. It's 15 inches from A to B here. So B is the, you know, the outer edge here. And we want to know what's going to happen to link number 2, angular velocity. Angular velocity is W, right? So it's W2. We want to place it on our diagram. We want to show it and we want to label it. So how do I show a W2? Just like that. Yeah. So we're going to have it like it curves around. Okay. It's going to rotate around. Now it's either going to go clockwise or counterclockwise. And that's going to be determined by, didn't tell us which way, by that straight line velocity. If that straight line velocity, the velocity at B is going down and to the left, do you see how my rotation, my angular velocity of link number 2 has to go clockwise? Right? Because if I put my finger here and I pull in this direction, that's the way that the rotation is going to go. So you could do that as well. Okay. And this is equal to VB. So if you want to add that. Okay. So W2 is what we are solving for. What's the equation that I'm going to use for this? I said the equation, not the numbers. Yes, you have to write your equation in variable form first. I want to know what you're doing. Okay. So even though the base equation, if you would, is W is equal to V is equal to RW, just putting it in V or W is equal to V over R, totally fine. Okay. It's just a rearrangement. All right. And now we're going to show, now Mitchell, tell me what my numbers are. Oh, well, here, Because this is, you didn't rearrange it, did you? Because I think you use this version, right? And I rearranged that to be W is equal to V over R. So my VB is going to be the 250, right? Inches per second on the top. Divided by 15, right? I thought you were here. Divided by 15 inches, right? Okay, that's fine. That's fine. Okay. My inches cancel, right? Top to bottom, and we end up with nothing per second. So my W2 is going to be equal to 250 divided by 15. What's my number? Yep, 16.67, right? And my units are going to be radians per second. All right. Now, the problem asked. Now, did everybody get 16.67? I did. Make sure you get that. Okay. Now, the problem wants us to know, determine the angular velocity of link number 2. So my final answer, 16.67 radians per second, put a box around it and label it W2. I'm not done. I'm not done. Why am I not done? I want to do what? It's not gonna like, if I want to put a motor there and I want to drive that and I got to find something that's going to, do 16.67 radians per second, I'm going to have a hard time finding those units. So I want to convert that into revolutions per minute always. Okay. So always convert. If I'm asking you, or if a problem is asking you for what is the angular velocity of, or what is the rotational speed of a link, and you end up with that radians per second, you have to convert this to revolutions per minute. So we are going to do that work here. So go ahead and do your conversion to revolutions per minute. And then once you have this in RPM, now it's a final answer. So then you want to label it W2 is equal to 159.2 RPMs. Did anybody else, make sure everybody else got that number? I didn't do it a second time to double check it. Okay, questions. So really kind of, two different looks here. This one was determining the straight line velocity V using the information here. And then this one was determining the angular velocity having or given the straight line velocity. Okay. All right, turn the page. It's more fun. All right. This is kind of a good problem, okay? This kind of looks at all the different points. We have a link. So this is a solid link here, all right? Kind of like triangle-y, okay? And it's rotating about point A. Point A is fixed on the frame. And it says we have this link, it's going to rotate at 15 RPMs clockwise. All right, determine the following. All right, so let's draw our W up here. All right, so 15 RPMs clockwise, that means we're going like this, right? W2 is equal to 15 RPM. Okay, 15 RPM. Now, if I wanted to know what the rotational speed of point A is on here, what is the rotational speed of point A? It's nothing. It's at 0. This is the center of rotation. And we wouldn't even say 0. It's not really a number. It's like non-applicable. Do you know what I mean? It's like it's not rotating. It's the actual axis. So I get, if you put 0, it's fine. 0 or NA. Okay. Now, when we look at the rotational speed of B, what's its rotational speed? It's out here. It is the 15 RPM. It absolutely is, because all of the points on that link, as we said earlier, they all have the same rotational speed except the center of rotation. So this is going to be our 15 RPM. Yep. So that means the W of C is also 15 RPMs, right? What about the rotational speed of link number 1? That one we can say is 0. That's the frame. It doesn't move, right? That one we can say is actually 0 or non-applicable. I would say that. I think that could be fair to say that. What about the rotational speed of link number 2? What is it? 15, yes. 15 RPMs. Okay. Now what I want you to do is try to label each one of these V's, okay, before we find the value. So up on our diagram here, show VA, VB, VC, V1, V2, okay, if you can. And some of them, maybe you're like, oh, I don't know what to do. Some of them you'll know what to do. What are you doing? So as we look at velocity of A, can we put a straight line velocity vector at the center of rotation? No. So we're going to put that NA, okay? What about the velocity of point B? Straight line velocity component at point B? Yeah, yep. Since this is going in a clockwise direction, I would show my velocity of B perpendicular to the radius back to the center of rotation. So this is B's radius of rotation back to here. It's going to be perpendicular to that line. And then velocity of C, that's also out here, right? This is going in a clockwise direction. Its radius back to the center of rotation is from here to here. So its straight line velocity is going to be perpendicular to that line. And this will be VC. Okay, so direction wise, we see that. What about the velocity of link 1? Definitely 0. And then the straight line velocity of link 2. That's non-applicable as well, because when we have an entire link, it doesn't have a straight line velocity component. The points on the link do. Okay. Now we need to get to, we get to calculate these two values here. Okay. So we know that the equation for this is going to be R times W, right? W2, and this is going to be R to point B. And then this is going to be the same thing, the radius to point C, but it's going to be connected to W2. Go ahead and solve for that. You may have to like get another piece of paper or do it off on the side here, okay? So go ahead and solve for the velocities of B and C, the actual numbers. as you kind of go through yours and you compare with what I have up here, I do have the answers here. Hopefully they match. So first things first, you got to convert your W2 to radians per second. Should get 1.57. And then plugging that into each one of those values, multiplying it by its radius from its center of rotation. You should get VB equal to 6.28 inches per second and VC 3.93 inches per second. Did everybody get that? Or same values? Any questions at all? Okay. Okay. All right, we're ready to turn the page. Okay. Things to remember. Things to remember. You fill it in first. What are things that you have to remember? Go ahead and fill this in both places. And then we'll go through it together. We'll talk about it. Okay, I'm gonna let you write your thoughts down if you would. Bless you. What are the two equations for straight line velocity? Two equations for straight line velocity. B equals D over T. That's when we're talking just what we call rectilinear, meaning like that box on the conveyor, the car on the road, walking down the street, right? How much distance do we cover and how much time did it take us to do that? Correct. What's the other equation that we saw here? V equals R times W. R times W. So this is what we call rectilinear. Okay, or linear velocity based on, it's just straight line motion, okay? And this is going to be based on rotational motion. Meaning it's a component of something that's rotating. So it's a point on a link, for instance, and it has that linear velocity component when that link is rotating. What are the units for velocity? I'll start writing. Inches per second. What else? Miles per hour. What else? Feet per second. What else? Meters per second, and so on, right? Whatever units of distance we're dealing with divided by whatever units of time that we're dealing with. Now, and direction, I'm going to say related to rotational motion. How do we know the direction of straight line velocity component of a point that's on a rotating link? How do we know it? It's perpendicular to the radius of rotation. Now, additionally, and it's pointed in the direction of what? Rotation, exactly. So we saw that the direction of velocity is always consistent with the rotation direction. So for instance, if we go back and we look, well, we could look at that one, but at these two, they're in opposite directions. For example, example number 2, notice W2 is going clockwise and the velocity B is going down and to the right. If I go on my, if I hold on my center of rotation and I pull in that direction, those two are related. If I go up to the top here, my rotational speed of my link number 2 is going counterclockwise. VB is going up and to the left. And again, if I you know, have my center of rotation at A there and I pull in the direction of the velocity at B, same thing. They go in the same, they're like aligned, right? They're aligned. So don't forget about that direction. It's in the direction of rotation and perpendicular back to that center, to its center of rotation. Okay, angular velocity, what's its equation? W is equal to, if we solve for W in that base equation, it's really the rearrangement of this, right? W is equal to V over R, right? Or if you put V is equal to WR, that's fine, okay? What are the units for rotational speed or angular velocity? Those are the same things. Radians per second and RPM or revolutions per minute. Correct. Yes. Direction. It's going to be one of two things. Yep, clockwise or counterclockwise. Whoopsie, counterclockwise. Good. See, everything you need to know. All right. Turn the page. Very last thing here. We got two small little examples, super duper small. What I want you to do for example number 4, draw in the velocity, straight line velocities of point B for each one of the links. And then down here, example number 5, draw in the correct direction of the angular velocities, the W's for each one of the links. So go ahead and do that, and then we'll compare. I'll give you a chance. Got it? Piece of cake, right? So tell me which way I'm going with my VB here. Am I going up and to the left or down and to the right? Down and to the right, perpendicular to its radius back to the center of rotation. What about VB here? Is it going to go up and to the right or down and to the left? Up and to the right. Yep, perpendicular to. Okay. And this one, am I going left or right? Going left. Oh. There we go. And then the perpendicular sign. Down here. Clockwise, counterclockwise. Clockwise. All right. W. Oh, well, we'll just do W. What about here? Clockwise, counterclockwise. For the middle one. Clockwise. Good. And then on the very last one, clockwise, counterclockwise. Counter. Yeah. Cool. That was fun, wasn't it? Yeah. Let's just go back to our PowerPoint. So I kind of pulled this out here because the book is very light to just kind of get all these concepts in, and these are kind of the foundation. I want to make sure that you have a good handle on this before we start going to the next step. Okay, before we start going to the next step. So if we go back to our PowerPoint, let's just kind of see where we're at and make sure we kind of hit all the highlights here. We talked about velocity on a link. Yep, straight line and rotational. We talked about angular velocity W, what its units are. And then doing those conversions. Okay. Here is converting between degrees per second to RPMs. We know that there's 360 degrees in one revolution and 60 seconds in a minute. So that was the, if you would, an example. Relationship between linear and angular velocities. Here's that equation. V is equal to R times W. It's equation 6-6 or 6.6 on page 126 in your book. Okay. And then it's just showing here that V is that linear velocity, millimeters per second. If we're using metric, our distance then would be in millimeters, the distance from the center of rotation out to that point. And then angular velocity needs to be radians per second in and out of that equation, what we've been emphasizing, okay? Angular velocity must be in terms of radians per second for that equation. And then the linear velocity will always be perpendicular to that radius of rotation and pointing in the direction of rotation. And then this is just kind of like you're converting. So it was, I think they have 2 examples in the book where you want to convert, but we did plenty of that in our handout. Okay. So that really takes us to kind of being done with part 1 of velocity analysis. Okay. Velocity analysis. I don't think I've put the assignment out there yet, and we're not ready for it. So I'm going to make sure that I'm not going to put it out until probably early next week. I want to be sure that you're focusing right now on the other 2 assignments that are out there. I don't want you to feel like, oh my gosh, I've got another thing to worry about. Just worry about getting done with the module 1. They were the kinematic diagrams, and then module 2, which was the velocity or the vectors that we looked at on Monday. Okay. Both of those assignments are due at the end of this week. So I want that to be your focus, finishing those up before we even think about worrying about this stuff here. Okay. So we just got to start on this next chapter. So I'm going to stop our recording here for now.